Gentlemen, this has been one hell of a year. 2025 has come to a complete and total end. Let me just simply start by saying we. The term we, when I say we, I mean a lot. My supporters over here on Patreon, when I say we, I'm usually referring to the team of people that are behind me that help support me. And the supporters on Patreon are a large chunk of we. When I also say we, I talk about all the people's lineage that comes before me that I've gotten to work with and learn from. Starting with the kindness of my friend Prime Minister, and him wanting to help grow me. And he just came along and started grooming me for what I do now. And I'm eternally grateful for him, because without him, a lot of the doors that I have open to me today would not be open to me at all. So I like to give him a lot of credit, because a lot of credit is due with him. Another person that I like to say we, and you're going to hear me refer to this a lot as we in this conversation, would be Tony over at Fatboy. I don't know if you guys realize this or not, but 90-ish% of the components that we use to do what we do come from him and his business that he runs out of New Jersey. So people can say whatever they want, whoever did whatever first and all this other stuff that goes on. But at the end of the day, our number one cabinet manufacturer, number one heat sink provider, and number one board manufacturer in the United States is Fatboy. And I would say a good 70% of the internal components that we purchase here in the US market for what we do to build products like this come directly from him. And a large portion of what I'm going to talk about here today directly ties back to him and his desire for innovation. Okay, when I say I say this very humbly, because there's no other way to refer to myself in third person other than to simply start saying BBI, and to me that's kind of narcissistic and hollow and wrong. So I'm going to use the term I a lot and we a lot. The other company that I really want to entity that I want to say thank you to is North over at HG, Haigu International Technologies. This last 18 months has been a lot for me and him, and we've worked through a lot of huge problems to get to where we're at now. And one of the main topics of conversation is that we're going to talk about the very first major step forward in RF amplification in probably the last 18 to 20 years. This is a big deal. In my mind, this is a huge deal. But that comes with some caveats, and we're going to cover all that shortly. This year has been an amazing year for me, because I entered into a kind of quasi-limited partnership with our friends here at Amprex. I can't get over how important it is to me, and it should be to you in the radio hobby, that we're able to still get these things made. I had a lot of fun getting to show the very first actual production Amprex, Penta Amprex tubes that were in the market. Everything that had been out till that point was a pre-production tube. This is a post-production tube. A tube just like this, I've got it actually mounted in a lucite case, and I'm going to send it back to Penta here just this next month, of the tube that we put 9,500 plate volts on, made it do 4,500 watt dead carrier, and then we proceeded to turn around and back that up with a 1 hour continuous 500 watt carrier from the same tube. I want to thank you, Penta, for letting me work with you and be able to help represent your company, and I thank you for your guys' support. Penta, in turn, has now furnished me with a set of every single tube that I could ever dream to have as test articles here for me in my shop. Not just limited to the pair of 3500Zs that are on my workbench over here right now, which we've all seen many a YouTube video on, but we're talking everything, 8877, 250Bs, everything. Everything in their inventory that I would use in my common day-to-day practice, they've really stepped up. And when I say I stand behind Penta, I stand behind what I see and what I know is tested, and what I have tested here and what I know is true. So Super shout out to our friends over at Penna. Scott, you are the man, and I'm talking about Scott at Penna. Please, if you guys go buy tubes from Penna, make sure to use the BBI promo code. It saves you guys money. I don't get anything out of the deal whatsoever, financial kickback or nothing. I simply am promoting them because they're about the only decent viable option that we have left here in the United States. So if you use the promo code BBI, you'll save 10 to 15% depending on what kind of tube it is on every single thing in their entire inventory. So gentlemen, let's get down in the weeds of this. Let's talk about where I've been, what we've done in this last year. It has been a lot. I've been all over the United States twice. I spent 2.5 months of this year on the road traveling, getting people back on the air, delivering products, picking up products, modifying stuff, fixing things. It's been a busy year as far as travel. It's been a busy year as far as new product development. And what I mean new is I mean literally no one on earth. We're going to cover that in really fine detail. And it's just been fun. I've been a little upset with myself. I haven't been able to keep up with the production schedule that I was keeping last year as far as repairs. I was only able to squeak out 62 repairs out of the 74 that I took on this year, or this last year. That's going to change. We got some huge announcements coming for that. I'll be talking about that here towards the end of the video. Like dramatic changes as far as this space is concerned and what we're going to be doing here with this business. Nothing but positive growth. So if you're interested, stay tuned for that. And oh, the old bag of transistors. This is a 1-gallon bag. This is the third one that I've filled full of transistors that I have changed out of different amplifiers that have been here for repair. I would say a good solid half of these are some of the things that we went and pursued this year to try and fix. Some of the failures that are in some of these transistors, we have thoroughly addressed that and changed things for the better, I personally feel. So sit back, relax. Let's get on with story time. Gentlemen, let's roll. That bag of transistors just keeps getting bigger and bigger and bigger. And the goal is to make it so that that bag doesn't get that much fuller. Let me start off by talking about the elephant in the room. Hold on a second. So like I was saying, let me start off by talking about the elephant in the room. Been a hot minute since anybody's seen these. I see a lot of people on Facebook these days wandering around and they're, ooh, I found a bunch of Toshiba man, I got 600 plus of these here. And I bought them way back when they were $75 and I kept buying them until they were $200 and some a piece. Look, it's just a part. Just because you have the part doesn't mean anything. I learned that very early on in this business. I want to really emphasize one more time that as I'm talking with you on video today, I am stating this as a fact. As I'm talking to you guys on video today, I'm really trying to come at this from the most humble point of view that I possibly can. I'm really excited about this. This has been a lot of time that I've been keeping this under wraps. Even the people that are really, really close to me, I've been giving them a wrong part number. I've been calling the new part a different number, which I'll cover here in a few minutes. But this has been a lot. This has taken a lot of time. I've got one project that I'm going to show you at the end of this that you guys are just going to be gobsmacked over that is arguably the most expensive thing I've ever built as far as a solid state transistor box goes. And that's saying something from somebody that's built everything from a 64 pill on down, 96 pill, 128 pill transistor. I've done them all. Either repaired or built them from scratch. Every single thing, right? So for me to say that is a pretty big statement. This has been a year of learning, a year of education, and a year of experimentation on my part. And I want to once again thank North and thank Tony for starting me on this path. So let's talk about the elephant in the room. I hear this often, frequent, and a lot. Why can't we just get the Toshiba remade? The 2879 Toshiba. Well, let's talk about that for a minute. So in this world, we have these things called laws. And I know that we like to look at the Japanese market or the Chinese market space as there not being laws involved with certain things. It's absolutely the opposite of the case. There's a lot of laws and there's a lot of rules that are involved with the Chinese manufacture of a lot of different things. Did you know that in certain countries like Japan, the Japanese government has went and sat down with the Chinese government and secured rights so the Chinese market cannot legally copy anything that they've produced without license and royalty fees and that kind of thing. Basically a non-copy compete with certain things in Japan with China and China with Japan. We would have the same thing in this country, but the leadership that we have in this country has spent quite a lot of time thinking about other things that aren't as important as trying to, well, under support the main manufacturing core of this country. So legally, the only country left that's manufacturing transistors that is willing to do with business with us and our market share, which is incredibly small, by the way, you guys, come to find out, there's some serious laws. The question has been thoroughly put to the universe of let's copy the 2879. Yeah, there's no more copyright here in the United States. This is true. If a company here in the United States wanted to go make a 12-volt bipolar transistor, which no one ever will, there might be some things that go on in court. I don't know. I'm not a lawyer. I'm just simply saying that that is not an avenue that's ever going to get pursued in China for a myriad of different reasons. So we need to just let that go, and we need to focus down on what we can actually get our hands on and work with. So, that being said, let's start down this rabbit hole. The rabbit hole is deep, and at the bottom is Alice and the rabbit, and they are definitely smoking a doob and maybe doing a line off a mirror, but let's go down to the bottom of the hole. Now, let me talk about something else real quick, and we're just going to hover on this topic for one more second. There's going to be people out there that are going to call BS on what I just stated about the transistor. So in China, come to find out, it's not what's actually printed on the case of the transistor, it's the actual chip design inside that everybody's concerned with. So when you get on eBay, that's why everything is labeled and it's a giant unorganized mess when it comes to false parts and the import of parts into this country. No one over there recognizes the part number on the actual case as being something that they're concerned with. It's the legal ramifications of the actual transistor design and the copying of the transistor design. Let me just put that out there. So if you're basing your BS call on me about what I just said about the copying of parts based off of your massive research on eBay, you're wrong. Everything on eBay and Alibaba is not genuine. And we thoroughly covered this a couple years ago when I went and I bought two Toshiba transistors from every vendor on Alibaba, eBay, AliExpress, Wish, every place I could find them, and they all turned out to be fake. There was a couple really good close copies, but then come to find out those transistors are actually made by a company that's now gone defunct that was in India. But that's a conversation for a completely another day. Let's get back on topic. So what we have here is, if we look at this part number, you'll see what generation this is. This is a 2SC2879, then another big long pre-prototype production number, and then the part number 16D08. This comes from the original test lot that was sent into the American market by North to many different builders to try and get everybody's opinion so he could match closer to the Toshiba transistor circuitry. And what I mean by that is the circuit that surrounds the component, right? The circuit that surrounds the component is just what it is. It's a singular part of a system that makes it's the core of making the whole system work, but the whole system has to be present for the one part to work. So what he was wanting to do was more closely match the transistor characteristics of the Toshiba with his own chip design. And this is, man, I don't know why I've held on to this for all these years, because this is back 2007, 2008. It's when we were dealing with the DEI scourge and a whole bunch of other stuff that was going on. The problem was that we had one vendor that was working exclusively with HG, and no matter what was getting sent to HG, the answer always came back, yes, much better, instead of simply saying, whoa, not so hot. So then when the rest of the community got involved, primarily Tony at Fatboy, is when we really got able to step forward as far as the quality of the components. So this was one of the pre-prototype transistors. It's not really relevant to today's story, but what is relevant is this is a current model 16D08. This is a current blown 16D08, and here is 2 or 3 generations back 2879C. So up here at the top, this guy here is one of the OG original pre-production 2879Cs that was sent to me by North for evaluation a long, long time ago. And at that time there was, he had 2 or 3 different vendors in the United States, and he had 3 or 4 different guys trying to help him prototype parts. We've seen everybody and their brothers show up and say, I was this, me first, and me then, and that's all great and all, but the problem is this part, it works, but it doesn't work that great. I opted not to pursue this transistor based upon my testing, and you guys have never seen me build a 2879C box ever here because of some of the characteristics that were involved with this transistor. So as we can see, the architecture between the two is roughly the same at a quick glance. When we actually start measuring things, and when I'm talking about measuring things is I'm talking about the thickness of the wafer die, otherwise the leads that come off the wafer itself. There's dramatic differences. We started running into a footprint issue here. And the other thing that we'll see that we're going to focus some energy on is these emitter shorting bars that take and equalize the amount of current load across the emitter tabs. That was a big problem, which we're going to talk about here in just a minute. The only reason I saved this component is for history's sake. I wanted to be able to have the opportunity to refer back to this part in the future when I got the part. So this one's never been put in anything. It's had an atlas and a Tektronix curve trace machine applied to it, and that's it. This thing sits just as it came to me. I'm going to slide this in here as well. Did you know that between this version of transistor and this one that we've adopted universally, there was a whole nother transistor that was in between the two? This is the 2879B transistor. This was developed for a company in Europe. This is actually the latest iteration of this transistor. We just got done doing all the product test for this transistor, and we increased its viability and operational life by almost 90% by tweaking some stuff on the inside of the cap. But this part number has existed forever, right? So this sits between this version of the transistor and this version of the transistor is this part number, the 2879B. It's not all that relevant here. He had a company in Europe that decided to approach him and talk to him about maybe getting a little bit more viable component than this developed, and this is what he came up with. He produced this for, and this is still a current product, by the way. He produced this for this company. He sent these to me in another test sample lot a year and a half ago, 18 to 20 months ago, and I started playing with these, and we made some changes based off of some things that I figured out here with this transistor. But all in all, the same things that apply from this transistor to this transistor to the new one that we're just getting ready to talk about now, all feed into the same thing. The emitter tab rod, this thing here, and this thing here has been the bane of these two transistor designs since day one. The problem that happens is underneath a large current load, you got to think that this consumes roughly 25 amps worth of current, and this one consumes roughly 35 amps worth of current, depending on which version you have. And by the way, we've tweaked this now. The last iteration of the transistor that has come out, or the generation before it, because there's been 2 new transistor modification changes in this last year with the 2879C, is just a couple different things. We'll cover that here in a minute. The main thing is that this tab, if you start measuring this with a micrometer, you'll notice that this tab here is significantly smaller than this tab, and that the thickness of the die wafer, the legs that come off the die, are almost half the thickness of these. So underneath a heavy current load, so we have our base, our emitter tabs, base emitter, and then our collector output tab here. The collector tab was getting shorted out internally from this bar, the emitter shorter bar, deforming and shorting out against the little tiny microscopic leads that make the attachment to the wafer leg on the inside. And that's led to a lot of failures. I mean, a lot of failures. Some of the testing that we did with the new component allowed us to adjust how this transistor operates internally, and I think we've got a much more stable component. I would not say all the bugs are worked out of this part, but I'll say that it is no longer really all that relevant in my mind. If we go and we fix this part, it's kind of been eclipsed and left completely in the dust at this point. So this is our history lesson. 16D08, about 9 different part revs between this one to the B, and then Tony did all the research and R&D for this one, the development of this, along with a couple other people that are here in the United States. I was lucky enough to get to be involved in that series of tests. I was initially very impressed with its performance because we were seeing 25 to 30% increase. The primary difference between this transistor and this transistor, outside looking in, is it's got a couple more chips on it. You'll see that there's a space here and a space here on the transistor that isn't occupied, that is occupied here. So from the 2879D or 2879C, we have the 2879D transistor, which is where I get to come into the conversation now. So chat, let's say the overall chat program where everybody was talking and working this out was primarily a closed loop between Tony at Fat Boy and North, right? 2 years ago, 2.5 years ago, I made a trip where I got to go back east to go be with my friend and hang out with my friend in New Jersey. And he was telling me about this new part. He sent me one to play with. I still have it. It happens to be in this particular box at the moment. He sent it to me to test. Initially very impressed with it, but then once again saw the exact same failures that we were seeing out of the C transistor for the most part. And I thought, man, that's kind of awesome. It's really neat. And then the subject just got dropped, right? We're both very busy people. And so I got to go back there about 2.5 years ago, and he had sitting there the 2879D transistor component version in a 4-pill format. And he said everybody and their brother had played with it, and they were all stuck at about 12 to 1500 watts at 12 volts. Now we're talking at 12 volts, not volting it, not overdriving it, trying to stay within the same drivetrain that we have currently today. Kind of like a 1 drive and 4 kind of situation, 120 watts ish going into 4 transistors peak, and we're talking peak numbers, not bird, going into 4 transistors. That day I sat down. This is my like 3rd or 4th day there. It was really quiet. There was nobody else there. Dottie was off. Saltwater Taffy wasn't there. This predates Danny being there all the time. It was just Tony, Brooke, a couple of the other gals that were in the office, and myself were there. And so he walks over and he sets the thing down on me. He says, let's see what you can get out of it. Set it down on the workbench. And within about an hour and a half, we were doing consistently 1700 to 1800 watts peak. Within about an hour and a half to 2 hours. Here's the problem, is that the amplifier worked like that for that day. We unplugged it as it was a working device, set it aside, and when Tony went to play with it, I think about a month and a half later, the amp wasn't working properly. So one of the transistors had failed in it. Armed with that knowledge, it just sat in the back of my head for probably a year. And I finally thought, you know what? It all comes down to time. Time is money, money is time. The hours on the workbench trying to figure out some of this stuff, that's billable hours that I can bill out to other people. But I wanted desperately to go play with these parts. I mean, like, desperately. So I finally called up Tony and I said, hey, you don't mind if I get involved with the development of this a little bit, do you? And he goes, no, I don't have the time for it. And he just didn't have the time for it. And I, to this minute, every single day, I'm incredibly grateful for him simply going, here you go. First, he was willing to share with me the top secret tech and let me play with it. And then two, he was totally willing to hand it off to me and say, hey, go play. So all of these amps, this represents about half of the test articles that I've built testing this stuff, are based off of that transistor design, the 2879D. We've come so far from the 2879D, it's not even a relevant part number anymore. I'm telling you, there's been the 2879D, E, F. See, how far do we go? A, B, C, D, E, F. I think we went all the way to J or I in different revs with different things that we've tested and changed and modified and played with. And at that point, that's when the whole 2879 part number just kind of, it's time we need to change the part number, right? It was getting ridiculous at that point. And it would have been very confusing for us to go from like I or J and then roll all the way back to D. There's a couple things that we have to overcome, right? So the first thing we have to overcome is this tab on the transistor shorting out. And then the other thing is if we keep stacking transistors, actual wafers inside of the transistor case, the body of the transistor, what electrically changes with that transistor that we now have to go address? Those are the big, in my opinion, the big elephants in the room, right? So without letting all the cookies out of the cookie jar, about 2 years ago, I discovered this absolutely amazing book. And I discovered it through YouTube. There was an amateur radio operator out there, name will be omitted, that had this book sitting on a shelf behind him on the video, and he did this little pan shot where he had just his head cropped and you could see this book in the background. I'd never seen this book before. It was written by Motorola, and I paused and immediately did an internet search for this part, or for the book, and that book is what really kicked open my mind on how to think about, from an engineer standpoint, the internal construction of the transistor and what characteristics we need to be focusing on if we were going to develop a new transistor, because it was a book that thoroughly covers the transistor research and design that Motorola did in the 60s and 70s. So from there, I was able to take a lot of that knowledge and be able to carry that over to this project as well. So I contact North and I tell him, you know, hey, I've spoken with Tony. I'd like to be read in on this project per se. Those of you guys that have ever had to sign an NDA, you understand what I'm talking about, being read in on something. Be read into this project, and what can I do to start helping? So the first thing he did is he sent me a batch of 4 current version 2879D transistors. I immediately put them up into this test jig. This is a pure inductor driven circuit for testing out components. The current one that's in this is a 2879B, and as you can obviously see, I took it all the way to failure. Okay. This style of amplification design is very, very, very narrow frequency driven, right? So let's say, because this one is based around the 27 megahertz band, let's say if I took this particular transistor and zeroed out our input capacitance and our output capacitance and our input inductor and our output inductor for channel 20, we're going to see the same RF response with the amount of power input from channel, like, let's say 18 to maybe channel 22. So from 27.185 or 27.185 all the way to 27.2250. That's how tight of a frequency that you can get with this. It doesn't allow anything else to come out of the circuit, right? So we don't have to worry about any spurious or harmonics or false signals. We do have to worry about our second and third order integer harmonics, but this is primarily suppressed in the circuit design. So immediately I saw the same characteristic failures with this transistor, but what I did see was a dramatic increase in power. So you can keep stacking chips underneath the lid until you can't get the lid on it anymore. The problem is the characteristics of the transistor dramatically change away from what everybody's used to working with. So our baseline, once again, is our Toshiba. Our Toshiba represents X amount of capacitance to the circuit and X amount of resistance. And the resistance was the thing that I was incredibly focused on. Once the resistance that the transistor represents to the circuit in operation gets too low, usually below 1 ohm, the part becomes very unstable. You can build an amplifier on a dummy load in a sealed loop system that will work, but once you try to use it in the real world application, below 1 ohm is completely suboptimal for real world operation. And so what we have here is this transistor. This is the 16D08, represents roughly 1.45 ohms worth of resistance in the circuit. So if we were to simulate the transistor in the board design without the part being present, we'd use a 1.5 ohm resistor to ground off the collector and the base tab to ground to simulate the part present. And we do the same thing with the amount of capacitance that's involved in the circuit too. And we'd take that directly to ground. And from there you can design the entire amplifier without even having the part in the board. When we started into the 2879C, I made the observation at that time that it seemed like it was very flaky. It seemed like it was about a 50-50 percentage working from being soldered in the box to actually operating. Part of the problem was this bar was too small. The other problem was that the die was too thin. The other part of the problem, and the main part of the problem, was that the resistance of the transistor was at 1.125 ohms. That's unachievable. To have a stable circuit around that is it's really tough, right? So when this transistor came along here, we can clearly see that there's yet another wafer of transistors that has been added to this, okay? The problem is now we are below 1 ohm. And the part, it's really hard to get a stable circuit around below 1 ohm. I cannot stress to you how hard this is. The tolerance of all the components around this transistor have to be so tight that it's not financially or emotionally or mentally possible to really get a solid working device. This is one of the very first 4 that I received of the 2879D, but the power performance out of this was just off the chart. There were some other hiccups internal design with this that was holding it back from making power. We see about 25% more power over this transistor. So we see about a 25% increase with this part, right? With this part, I was seeing 100% increase of output power versus this. And that was because he changed some things on the chip design to be able to make it fit underneath the cap. All those wafers. Look at all them wafers. See that? Now, to the sharp eye, you'll notice that our emitter bar has now been deleted. And that was one of the very first things that I said to him. No, this is version number 2, because version number 1 had a solid bar that went across the top. So one of the things that we did with the 2879C is internally he went and he would spot weld a bar that would go from the emitter tab to emitter tab directly across the top of the transistor, and he deleted this little punch dyed piece of metal because it was such a high failure rate. There's not enough room underneath the lid of the transistor to make that jumper between A and B, the emitter tab A and emitter tab B, on the new part. So we deleted that out of there completely, and our solution is that we would just go ahead and strap over the top of the part. So this is what we did here with this one here. You'll see that there is a piece of solid copper that goes from emitter tab to emitter tab. you're going to want to follow this idea if you ever choose to work with these parts in the future. Even though we've gone back now and we've changed that even since then. They're just not enough room underneath the lid. It's just not. As we all know, the foot of this transistor is different than the Toshiba. It's slightly bigger for reasons. But the surface area of the foot is our primary biggest struggle with this part. The amount of input watts, because remember that the transistor is only 60% efficient, the number of input watts of heat dissipation through the foot was our biggest bottleneck. And once we're able to overcome that by changing of the transistor design, I'll cover that here in a few minutes, the next biggest bottleneck in the circuit was its resistance, what it represented to the circuit in resistance and operation. As I was going forward, everything I would do as a test, I would have the actual curve trace data test and not the stuff from the Atlas. The Atlas is a great component tester. It works really good for the home gamer. I've got a really nice Tektronix curve trace, the same machine that North has got. I went out and invested and bought one of those. I would do the curve trace data to verify what I had on my part, that the parts that when they left his place to my place, they were the same, and then I would proceed forward with very incremental tests, and every single thing was a very stepped, careful unit of measure. So first we'd start off at 12 and then go to 12 and a half, run a whole battery of tests to either drive and how the circuit changed, what the voltage changed, and on up all the way up to whatever top voltage he declared he wanted me to test to. Let that sink in for a minute. So it's not just hooking it up and going hello adios, and that's a non-valid test. There's too many variables in the circuit, right? There's the radio, jumper length, the circuit design, voltage, and all that kind of stuff. And whistling in the microphone is not the appropriate way to get any kind of data skew out of anything. This amplifier is an old whore. This thing has seen the 2879Cs, it's seen the 2879Bs, it's seen the Ds, the Es, and the Fs. The current iteration that's in this is the new part. You ready for the new part number? 2880B. For my friends that have been close to me, the part number I've been telling them is 3880B for a reason. I really was not able to talk about this until here recently. So the actual new part number is 2880B, and there is no 2880A. He put the B number on there for, or the B letter on there for, well, got a lot of time and energy wrapped up in these, let's just say that. This amplifier was taken to failure, and what I mean by that is we ran this to 250 watts continuous carrier on FM for an hour and 45 minutes, and the main thing that failed with this was the emitter tab came unsoldered from heat. This output coil came off due to heat. There's a lot of steps that took place between this and this. The main step that we came up with was changing the material make of the foot. So my initial idea was that we make the foot of the transistor something solderable. These are made from an aluminum mix and a couple other different materials, the foot of this transistor. The foot of this transistor that's in here is made from powdered copper, a couple other forms of nickel, and then it's nickel plated so that it is 100% solderable. When we did that, the ability of the transistor to cool itself went up dramatically. There's a lot of heat loss that takes place between the actual transistor foot, and what I mean by the foot is down at the die level, and then transferring through the layer of ceramic and then into the layer of metal. There's a great deal of heat loss there. As in, like, the part can't successfully wick enough heat away from itself and then transfer it to the foot and then transfer that to the aluminum heatsink. So the idea was that we would solder it down to a spreader, which is something that I pursued later on after we changed the transistor design. So now we're talking, this is 1, 2, 3, 4 different revs of this transistor at this point, because we're changing everything incrementally, right? So we'd make a small step and change something, either liked or disliked the characteristics of the transistor. It If we disliked it, we disregarded that transistor change, and then we made the next step forward, and then we would make another small test. So we're talking small batches of maybe 1 or 2 transistors. At one point we did 1 transistor test because it's expensive. It's my time, his time, and his engineer's time, the manufacturing process's time, plus then the cost of the case, then plus getting it here to the United States. Each one of these tests represents a lot of money and a lot of time on both sides of the ocean, right? All for what? A market that we don't know that we're going to actually be able to get the part into, or if anybody's going to be interested in it. So it's a huge gamble, and it's a giant investment in time on both sides of the street, right? Mine and his, and then on top of that, the giant investment of time that poor Tony had to sit there and listen to me talk about this for hours on the phone. Tony, you have the patience of Job. I appreciate you, my man. You are the man, right? So this was a 2 failure test, and this was for voltage, maximum amount of power, and time. And when we got to this point, and the failure point was the solder tabs, the actual leads that are coming off the transistor, I knew that we had really gotten to something. Some of the other things that we did internally, I can't talk about the very specifics of it, but I will say that we spent a great deal of time changing the wire architecture from the transistor to certain component tabs, and the wire material makeup is what allowed us to be able to increase the resistance that the part shows to the circuit, either it be on the base, from the collector and the base tabs. That the changing of the actual monofilament wires that are in here hooking up each one of the die chips, we were able to finally get this back to about 1.4 ohms. And the capacitance is almost back where the Toshiba is at. We're really close, enough that it's under 1%. And that 1% variance was really important to me because I got to think about the people downline from me that are going to be working with this if this does make it into the market for years to come, right? So I have to think about the other builder, not just myself. I have to think about everybody else that's in this same market share and wanting to be able to help cross-support them, right? So our goal is to create a component that puts out more power, but is more stable, more heat robust, has a higher SWR tolerance, right? Or output aspect ratio is the appropriate way to think about it. And it had a little bit more frequency diversity to it. And it was more stable, as in longevity, abuse, voltage tolerance. All of these things had to be addressed. Otherwise, I might as well just stick with this. Okay? And guys seem like they really like these transistors. And I think it's just simply because they do more. It ain't from a reliability standpoint, I can tell you that right now. I think everybody that's in the market that builds with these, at one point or another, has built a box with these, and I know that there's going to be the one guy, or maybe 2 guys that are like, oh man, I've never had a problem with 2879C, no, they're a great part. That's awesome, dude. The rest of everybody that's in the market share has built some of the most beautiful and elaborate amplifiers based around this part, and then immediately had them fail for some random weird reason, and they couldn't understand why, because it was at the component level. That's fact. Okay. If your amp builder is willing to, humble himself up enough to publicly admit that or not is completely up to them, and I am not going to call bullshit on them or call them a liar. I'm just simply saying that the majority would simply say that this part is good for what it does. There's better out there to be had, and there's definitely better out there to be had now. So we've gone from a 120 watt part to roughly a 200 to 300 watt part. From the Toshiba to this, to this, to this, to now this. And I can't wait for all that information to be verified with other builders. Now, I live in a little bubble, and I know that. And I've said to North from the very beginning that I want to help develop this part, but really where the rubber meets the road is when it gets out there to other builders. I cannot put the necklace around my neck saying, I developed this part, it's all me. It's not. None of this works like that, and it never will. So I don't want to hear from anybody saying, I showed up on video claiming this, that, and the other thing. It's not the case. And the attitude has always been and is going to be that we need to take a small sample batch of these, and we're going to send these out to, when I say we, I mean him, is going to send these out to a couple different builders across the United States and let them play with them. Now, if you are lucky enough to be part of that test sample, you might want to pick the phone up and give me a call, and I will openly and freely share with you every single little bit of knowledge I've figured out about this part, and I'm going to help you with every bit of my soul to try and be successful. That's an honest to God fact. I'm not going to hold anything back from you. I'm going to tell you this is what we've figured out works. You might want to try and emulate it yourself. Now, let's start talking about what all these different boxes represent and the different iterations of what we've done here and how that might actually help somebody in the future. People are going to want to build with this part. There's no ifs, ands, or buts about it. Is it going to replace the 2879C? I feel it's the 2879C is of this moment officially dead. Is it going to continue on and get built out? Sure. There's boxes out there that have been contracted right now as this minute to be built with the 2879C. Is the 2880B available to the public yet? No. I'm hoping that we can get it out sometime this year. But it's got to go through everybody else's hands first and everybody else get comfortable with it, and then we've got to listen to what everybody else's feedback is. And everybody else's feedback is just as important, if not more important, than what I have to say about anything. I can't come out and say this is the greatest thing since sliced bread, because in my world it's the greatest thing since sliced bread, but I live in a bubble. Other people build completely different, and they're going to expect different things from the transistor. So we have to hear what they have to say, and those parts need to be tested by other people, right? So let's stop looking at these and let's go talk about all of this. So as of this moment, the latest iteration of this transistor, the 2880B, is 25W32. That's the latest iteration. This part number here is a 2880B, and this is 24W46. By the way, I actually asked him one time to break down all the different transistor rev numbers, and what I got back was a giant freaking spreadsheet that was about 35 pages long of different part revs that he's built through. Okay, so these are our two product test samples that we just do one or two transistors at a time. I'm going to skip over a bunch of the other transistor versions and just go right to the product that was working, that we finally got working. So let's start here. I built this 0423 2005 2880B. The transistor rev number on this is 25W13. So like I just said, we're already at what, 25W32 at this point. So this is a little bit dated. This amplifier design here is what I did the max carrier continuous heat dissipation tests and runouts with, and did transformer core size testing with. Right, so what we were searching after was transformer saturation point, heating point, and how much heat we could actually get rid of the part, off the part. This is also a solder paste-free environment above board. If you can see, there's a big copper spreader that's underneath this board. So we got to utilize the entire heat sink. Please note the strapped transistors. Do not use solder wick. Do not use braid. Do not use a phenolic board. Just a nice, decent 22 gauge or bigger piece of solid copper strand will work just fine. I saw a lot of interesting characteristics with this that we would not ever see normally with any other transistor based kind of thing. I saw a phenomenon take place here that I've never seen before. Please note there's metal clad capacitors on the output transformer and the input transformer. Myself on video actually have a video where I was sitting here running this amplifier at 500 watt carrier on FM, and the input transformer capacitor caught on fire. Yeah, let the smoke complete out of it. The part, fine. The transistor, good. The capacitor that was here, and it was 1,000 volt, 1 kV, it decided it didn't want to be here in the circuit anymore, and it just let the smoke clean out of it. The other thing that I had is that the face of the transformer was getting so hot that I had several parts fall off. I've talked to everybody in the industry over the last several years, and I said, have you ever had this characteristic happen before? You go, no. No, we never have. What? Wait a minute, what? We see that on the output transformer from time to time. We see it actually quite often. If you use too small of a part, too small of a capacitor here as far as its kV rating, it'll fail. Depending on where you put the capacitor on the front of the transformer, there can be some eddy current heating that takes place, and the part can fall off. To see it on the input transformer was something phenomenal. You'll note that the board is cut in half. The reason the board is cut in half is because I have to put the spreader down and then put the board underneath the transistor, and then, because remember, transistor soldered to spreader. It's the only way we could get enough heat off of this. This amplifier here, I mean exactly what it says right on the front. With the right situation and the right voltage and the right amount of drive, we were able to achieve 1,000 watts peak out of this tube pill. It's a thing. That's the world that we live in at this point. If we choose to adopt these transistors as a body of people, that is a world that we live in. Now, to get this thing to stay together, in all fairness, the volume of air that was having to move through this thing was significant. This thing sounds like a little jet engine when it gets up to speed, and you're not having a conversation on the radio when this fan's running. But that's what we had to do to get this to hold together. So is this realistic? Like, can we go build a banging 1,000 watt 2-pill for everybody? No. The drive chain for this to get enough drive into this to achieve those numbers was very interesting to me. It was 1 drive and 2 drive and 2, and it wasn't in a competition state neither. Serious. Dumping a ton of drive into this box, and the way you got to modulate all 3 of the amplifiers together to get that high number is a little bit tricky too. But I mean, this is a solid 500 to 750 watt amplifier all day. Does it need to have this aggressive a fan at that level? No, but the main thing is that we're doing it on FM. So you have to think in AM mode, there's pulse in between your modulation and your bass carrier. So we're pulsing the component on and off, or surging into the component. Or FM is just, you have a solid block of carrier, there's no modulation peaks, the transistor's on 100%. It's harder to build to the FM standard than it is to just peak. Even when you're whistling into the microphone, it's not a pure sinusoidal wave and blah 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 blah. This was neat. When we cracked this egg and we got to this point, I knew that we had ourselves a hot ticket, because it could hold together, and it would just run and 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 run. So immediately, and these are all pre-production parts, by the way, so I don't really know what we're going to get when it comes to actual production components. That's another thing that I want to talk about. Is so in the industry as a whole, you have pre-production components, and then you actually have production components, and I don't think you guys quite understand. So when you're talking, we're going to make, well, let's use Amprex, Penna, or that kind of thing. If you're buying out a pre-existing company, you have their old product run that was built by who knows who, by who. Those are all pre-production. When you get to production, that's when you actually get to see what you've got for meat and potatoes on the road, right? So right now we're just talking about, we're researching a transistor and to see if it's possible, When you decide that you're going to move to production, you're going away from one person sitting at a workbench, preferably in a quiet environment, and giving it 1,000% of their attention, and very bespokely putting one transistor together at a time. You're going to have a higher success rate in a small batch number pre-production run than what you're going to actually have in production. When you're in production, there's 20 people, maybe some dude sitting in the corner smoking a cigarette, a little monkey over beating on a drum in the corner or something, I don't know, TV blaring in the background, everybody's talking about what they did with their wife or their significant other the night before, in your manufacturing transistors, right? Is the quality of the assembly process and the quality of what you're getting in production exactly the same as the one-off, very carefully assembled, bespoke, pre-production piece of? No, there's a difference. These are all pre-production units. These are all research articles and test articles for us to be able to go through. And I'm not kidding you, I could double down on this yet again, of more boxes with more parts in them, with more dates on them, more and more and more, and more and more and more, if I wanted to. I've saved every one of the test articles for me to be able to refer back to. I have 3 binder books that look roughly like this, that are completely full of notes off of these test articles, right? So I knew we'd hit the jackpot, and so I immediately went and I wanted to do this. This is still sporting the 16 DOA part number, but this is the 2880B, this one here. I don't know, some of you guys caught it, some of you guys didn't. About 5-6 months ago, I did a video called Much to Do About Nothing, where I sat around and I talked about my wife's birthday and my truck breaking down, and in the background I had that meter pinned in a corner with a 1,000 watt carrier, and the video was about 40 minutes, 30 to 40 minutes long, if memory serves me right. I'm probably wrong, it was probably 20 minutes, 29 minutes, something like that. I just sat there and talked with this amplifier being cooled by this standard 0.3 of an amp fan. One of the heating sensors for the HVAC system in the truck. Other than that, there's no codes. All we know is we got this mystery 1.7 amp continuous 24/7 365 all the time draw that goes on. And I just left it keyed in FM, just full chooch 1000 watts. Several points in the video I had to keep backing the drive down because the hotter was getting, the more power I was putting out, and it kept creeping forward. It creeped up to like 1200 watts, 1300 watts carrier. That's this amplifier right here. This is the inside of that amp. This is the same amp that I took all the time when I did the frequency expansion envelope. So primarily up until this point, we had focused strictly on the 27 megahertz band. I'm not going to lie, I got an ulterior motive involved in this. I want to have a part developed for me, my personal use, for something else that I'm planning on doing in the near future, and I need that part to be able to operate other places, right? So as part of the test platform, initially we had to figure out where the transistor would run and where its bottom end of frequency and its top end of frequency is. And I'm here to tell you on the data sheet, it's going to show 0 through 30 megahertz. And when I say that it is 0 to 30 megahertz, it has been tested from 160 meters all the way to 6 meters in this cabinet. Today's date is 3-4-2025. 4 new prototype transistors. As we can clearly see, there's nothing else in here. So what we have here is the amp draw, volts on the box, 1000 and 2x in peak, 1000 and 2x. Well, here, we'll do it like this. 1000 in average, 1000 and 2x, so 2000 watts. 50 watt element going in. We're hitting it with the workbench, 4-pill, straight 4-pill. Hello, 1 1 1 1 1 1 1 1. 750 watts of drive. Produces. Hello, audio. Just around almost 900 bird. In 1937 is what I saw out of it. Hello, 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 hello. It's the only reason I kept this cabinet. A lot of time here. I've had to change the transformers in this a couple times. The windings in this have changed quite a bit. The capacitance values on the input and output transformers have changed quite a bit. That's the reason I use tuning tubes here, so I could change things back and forth as I needed to. This is full class B, by the way, biased. I also did all the bias current expansion growth on the transistor here as well. We know the high and low range. It works perfectly good up to just under a volt, and we can maintain really good operation down to 0.28 of a volt. Honest, and it stay within what we needed to see out of the part. This was, I've spent a lot of time inside this box in this last year, but this is it. This is the much to do about nothing amplifier right here, which I thought was amazing. I've been letting little tidbits like this amplifier. The guys on Patreon got to see a video with this. Of course, there was no information added along with it, and then they got to see little videos of me testing different things with this one here. Of course, there was no information added to that as well. It spent a lot of time thinking about this part in the last year, I'm here to tell you. And once again, I'm just absolutely humbled that I got to be involved in this level. So I built this, and that's when there was a fatal flaw discovered in the system. So this is an 8 transistor amplifier. This is made with the 2880Bs. This is version 25W12 for these parts that are in here. We had very good success with these transistors, and so I went, okay, let's double down and let's go be able to focus ourselves on good stable bias control, and let's start thinking about adding another layer of combination and splitting to it as being the variable in the test. And what we ended up having here was some random interesting harmonic failures, and it came down to a bias issue, and then it came down to, and when I say bias, I'm not talking externally to the part, I'm talking on the transistor itself, that didn't expose itself until we went and built this box. And this really was confusing to me and the engineer at HG as well. Spent a lot of time chatting back and forth with him about this and what the characteristics of the transistors were that we needed to change. A great deal of time. This was a huge wall of frustration, because until we could overcome the internal bias control issues of the transistor in this low of a capacitance environment, an inductor environment with the splitting and the combination of the circuit, we had hit a brick wall. We literally had hit a brick wall. So you'll see once again the capacitance values have changed on the output transformers, input transformers. We overcame that. We were able to overcome that issue a lot, and I got this box working 100%. This one makes honest on 12 to 15 volts. Honest engine about 3,400 to 3,600 watts. This 8-pil peak power, and it does it very reliably. It's currently in the conversion of the state of Class C, but it has all been pre-wired for Class B. Okay, so we're coming to the end of this. I know I've lost half of you guys. I've been sitting here talking nearly for an hour. There's been YouTube videos added, words and things. We are going to show you some tests here in a few minutes, though, of course. So here we come to our latest version. This is the 2880B version 25W32. Please note, transformers are much smaller. These are built with the transistors that Tony's currently using over at ICA. And I wanted to do a head-to-head comparison, this one versus this one. I had to do all the transformer expansion growth in this cabinet. And what do I mean by that is I've tried my version of transformer, the standard 1-inch by 2.5-inch, you name it, they've all been in this cabinet. I've used Tony's input transformers. I pulled stuff out of old Fat Boys. I've pulled stuff out of old Dave Maids. I've pulled stuff out of old X-Forces. I've tried everything, and we've tried different sizes, and I've got the different capacitance values, and I've got the different number of winding ratios, and all that. We've done a 5-wrap tune on this, a 4-wrap tune on this, a 3-wrap tune on this, what I call a 1-to-1 wrap tune on this. We've done 5 and 3, 4 and 3, 2 and 3. I've managed to get 6 pieces of wire wrapped through this and measured the characteristics differences. I did a little bit of that over here, and I did a lot of that over here as well. But the primary thing here was I basically went out and bought a set of transformers from everybody that was in the market, and I wanted to really, really make sure that if somebody in the future went to build with these, it seems like guys are getting really hung up on, well, I have this style of transformer and that's what makes my amplifier better. There's a little bit to that, and then there's a lot of that that is not. Okay, so at this power level now, we have to be very careful about heat saturation into the transformer. In this current configuration, amplifier works great. It does about 150 to 200 watts less than this here. And it's because these transformers are oversaturated. There's too much RF going into the transformer. The transformer, the size of the wire that you have to use because of the smaller size of the tube, there's not enough field flux, there's not enough coupling that takes place, and when you run this underneath a FLIR, you've got up to 3 beads on the transformer that are starting to they're so saturated they're getting hot. which as soon as you start seeing heat in any of the transformer ferrite, you have lost. That is, heat is now being developed instead of it being coupled to the wire, and that's output power that's being lost. These transformers work great. They work great for the 2879C, the regular 16D08s, that kind of thing. For this transistor going forward, we need a little bit bigger bead, need a little bit bigger tube, and we need a little bit bigger surface area on the front of the transformer. So all of those things can be addressed easily, and it's not an issue. These transformers work great for all of our current existing parts. They work really, really, really well. I understand why Tony went to these. They work great on the combination side of things. I've tried it with a little 1/2-inch bead. I prefer to use these because there's no heating. Once again, you see heating in the ferrite, you're losing power. That heat that's being generated in that ferrite is lost watts that you're not getting out of the box. So having a FLIR or a thermal imager, very handy to have. And I think I said that 10 years ago when I first started dicking with the FLIR. I think there was a couple guys that were before me that had the FLIR and they were using them. Very, very, very powerful tool. Very powerful tool. So this is something to think about. The biggest tip that I can tell you is, because there's double the amount of transistor wafers from the 16D08 to the current part, is you're going to need to not use 10 ohm resistors, and the 120 picofarad capacitor is no longer used. You can make it work with 120, you can make it work with the 10. The 10 ohm is going to burn up. It's the wrong resistance. It's too high. And the 120 picofarad capacitor on the output side of things is too high. We have to think like half, right, in certain situations for things. That could probably almost be a universal blanket statement if somebody wanted to read between the lines enough, that we have to think along those lines. So let's hook up some stuff. Let's run some stuff. I want to show you this one running, and I want to show you this one running as well. And then after that, I'm going to let you guys go and send you on with your day. This is part one. This whole song and dance is part one, by the way. Because part two, we're still in construction of it, and it might actually come out after the first of the year. But this is part two. There's a 1/4-inch copper spreader underneath this custom-made board. This is anodized aluminum heatsink, which, as we know, is a better conductor of heat. I initially was going to solder all these transistors down, but since this is a test platform, it's going to be 4 drive and 16, so it's going to be 4 drive and 16. I wanted to be able to change out parts, right? So we didn't solder down the transistors in this thing. This has been a nightmare to build so far, but it's going to be neat to see where everybody takes this, the tech that comes from all of this and all of this, and see where other people take it. Because I know where I've taken it, and I know the numbers I've seen, and I'm very interested to see what other people can do with it. Because really, we do not have a viable product until we can come together as a consensus mass and say this is a good thing. I have to keep that in mind. But this is part two. This is part one. So let me get this back out of camera. Let's set up and let's actually run some stuff here. So here where we'll start is we're just going to take our standard Striker 955, our derail. It's not standard, nothing standard about that radio. Our derail 955 radio, our bench radio. We're going to put about 125 watts of peak into this, and we're going to run this at 14.8 volts. It's basically the same thing that you'd see in your car. There are some dramatic differences here, but they're very subtle. You will find that with your standard 2-pill and a Striker hitting it, you'll see about 500 watts. 450 to 500 watts in the real world. You want to see a fully saturated part, and you get at 500 watts all the time, you're going to have a 1 drive and 2. Okay? So with the amplifier off, hello, 1, 2. We're 1000 watt in peak here, 1000 watt peak here as well. Even though it never changes, I want to show it to you. So we're showing, hello, about 125 here, hello, 117 here. If I simply reverse the elements, put that one here, and put this one here. Hello, 1, 2. Okay, we'll see the difference in power. Let's turn the amp on. 200 watt dead key, by the way. Hello, 600 watts. And we're not volting anything. We'll flip this back around. So we've seen 590. Hello, audio. So we see that we're perfectly stable. Our input's perfectly flat. There's no weird spectral peaks that are causing the thing to read false. This is legit 600 watt 2-pill. Let's try something different. So we're going to put 40 more watts of drive into it. We've changed over to the Striker SR490. All our voltages, everything else is exactly the same. And so we're going to look at this peak number here. Hello, 1, 2, 1, 2. So we're up from 120 up to 160. So 40 more watts of input drive. Hello, 1, 2. We're seeing close to 200 peak on this meter. Hello. We're seeing a nice solid 700 over here. Hello. And 645 here. This is not volted. We're not doing anything crazy, and we're not putting like an astronomical amount of drive into this. This is on par with what we're getting out of the 2879C, volted and driven harder. Less drive, less volts, more output. So we're at 700 watts. Refer back to what I said just a few minutes ago on video. Hello, 1, 2, 1, 2, 1, 2, 1, 2, audio, 1, 2. 750 watt all day cruiser. Not volted. Volted, forget about it. There's some crazy stuff that goes on when we go up in volts. This is average every day. So what we're seeing is literally like a 100% increase in output power over the 16 DOA. And then when we volt it, it's off. The numbers don't even track. It's different. If I was to put more drive in this, we're going to see more out of it than this. But it's not relevant for this conversation. So let's move on to a different box. Okay, so once again, 1,000 watt slug and peak, 1,000 an average, using the 2880B 2-pill to drive the 2880B 4-pill. So I got the mic gain on the bench 2950 pulled way back. Hello, hello. See, about 150 watts max drive is all we're getting out of this 2-pill. And we're going to dump that into the 4-pill. Hello, hello. Okay. Go to 2x. So as we all know, all the way over here is 2,000 watts. Right here in the middle is 1,000 watts. Now we're going to flip-flop the slugs here in a second, but 1,400, no problem. Remember, we're still at 14.5 volts, 1,400 watts. So we'll flip-flop these around, and let's see what the steam and coax meter says. 1,200 watts, no problem. No problem. But if we increase the drive a little bit more, 1, 2, 1, 2, 1320. Hello, 1,500. It just keeps going. Now you can change the voltages around, you can do a bunch of stuff that you want to do, but I'm here to tell you this thing is a solid 1,500 to 1,700 watts peak 4-pill. not volted. Not volted. It's just food for thought. Just saying. This is a real thing. This has honestly consumed 18 months of my life, and I've got unknown countless hours and hours and hours working with this. Now, let's go to the latest iteration of this part. Okay, so this is the last iteration of the parts. This has got the output transformers on it, like we just previously spoke about. We're going to see 150 to 200 watts less, just from the transformer size. And yeah, I might show this on FLIR, but you'll see that when we start running this, the beads will start to heat up. And that, it's an oversaturation issue. But the point is that it's doable with the different size transformers. And I'm trying to do this so that other builders will be encouraged and not be frustrated to go ahead and try. You know what I mean? So, driver setup exactly the same as what we had going on before. Our voltage is the same. Our watt meters are all the same. Hello, audio. 212, 2500, somewhere in there. 12, 1250, 1275. Let's flip these back around. Hello. Let's go back in here for verification. Hello, audio, 1, 2. Just saying. It's consistently the same. The upside to these new parts is that they're incredibly stable now. We've got all the little bugs worked out of them. This version here, I feel that we've got all the bugs worked out of them. This is combinable to an 8-pill stage, and we're going to find about 16 here. We'll find out about that here before the end of the year. But for right now, and remember, this is not volted, and we're not being abusive. We're still putting 100, 150 to 200 watts of drive into this 4-pill. So we're not seeing crazy numbers, and also this is in Class C. Previous one was also in Class B. So we could pick up a couple watts by going to Class B, pick up a couple more watts by changing out the transformer size. You'll see. You'll see. It just keeps going farther and farther and farther and farther forward. But it was time. I felt like I've spent enough time on this, and I think it's time for us to start talking about it publicly, and I think it's time for us to start getting other people's opinions. And I can't wait to see the videos of somebody showing up saying they did this, that, or the other thing to help in the situation, or they saved the day because they blah, 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 whatever. However they want to try and play it, at the end of the day, it's time to let other people in on the conversation. I think that this is going to be the next new thing for all of us to work with. And in conclusion, remember, I started all of this to get something out of it myself. And the future is here. The future is here. There's more magic schmoo underneath the lid of this transistor. Maybe next year we'll talk about this. Gentlemen, I want to say thank you. This has been a wonderful year. I've gotten to work with so many different people and so many different companies, and I've gotten to help so many people. I've gotten to travel around this country and see so many different things. Got to meet so many wonderful people. Got to go hang out with my buddy Brian Smith. I got to go see my friend Zane. I got to see a whole bunch of you guys this entire summer. It's been great. I do not get to be here without your guys' support. I don't. I am humbly grateful that I've gotten to be involved in this project up to this point, and I really think that we've got ourselves something fun to work with here. I think that this is going to allow us to grow what we're doing. I mean, I would say the top end of this transistor is going to be in a 4-pill configuration close to 2,000 watts peak. But I'm going to leave that up to you guys to discover and figure out how to get there, and I can't wait to see the videos. I think this is going to be fun for everybody. It's going to give us all something new to talk about, and this is a giant step forward. Major shout out to my friends here on Patreon. I say this a lot, and I mean it seriously, the Patreons of what have allowed me to have enough free time to go out and work with these things of projects, shoot the interview videos, travel, do all of these fun things. And I say thank you to them for being able to let me try to work on projects that I feel are going to help support all of you guys. Super shout out to my friends down at Penta, our friends Mark up in Canada at Steaming Coax, D-Win, and those two guys. I introduced those guys, and the amount of work that those two have done with each other to help grow Steaming Coax's business has just been jaw-dropping to me. I love seeing all the pictures on Facebook of everybody putting their meters up there that they've built for their new stations, and it's great. I think that the opportunities that have been laid at my doorstep, I can never say thank you enough for being able to be available, to have them show up here and just getting to be involved, I think is amazing. And I humbly say thank you to the radio community for letting me be involved. Gentlemen, on that note, I'm going to go. This will be the last video that you see from me until 2026. I appreciate you, gentlemen, and I mean that honestly from the bottom of my heart. And thank you. I'll see you. Click, click.